limit comparison test. When the direct comparison test is difficult to do because you cannot compare term by term the two series, then the limit comparison test would be a better option. The requirements for this test are the following. The terms of the series are both positive, okay? And here's a condition. If we find the limit of one series over another, the limit must equal to some positive number L, okay? It must be a positive number and a finite number. That's not infinity, okay? When this is the case, then the two series either both converge or diverge. So let's look at this series here. The series of n all over n plus 1 times 2 to the n minus 1. Because the exponent is much powerful than the polynomial, we will compare this with the geometric series that is convergent. Okay? So as you can see, it's difficult to compare term by term the series terms, right? So we cannot use the direct comparison test. What we will use instead is the limit comparison test. I forgot to explain to you that the terms in both cases must always be positive, okay? So if you look at our series here, because n starts from 1, then the numerator will always be a positive number. This will always be a positive number. Anything raised to some exponent will always be a positive number. So a positive divided by a positive times a positive number will always be a positive number. Over here, 1 is a positive number, 2 raised to any power is a positive number, so both series are positive terms. What we're going to do is find the limit of this series over this series as n goes to infinity. If our limit is equal to some finite number L, then because we chose a geometric series that is convergent, then we can decide that this is a convergent series as well. So we will need some algebra here. Let's simplify. We can rewrite this as 2n over n plus 1 times 2 to the n. Where did that negative 1 go? I put it as 2 in the numerator. Divided by 1 over 2 to the n. And then dividing this, we get 2n over n plus 1 times 2 to the n times, we will now reciprocate this, 2 to the n over 1. We notice that we can cancel this. And so we get 2n over n plus 1. Okay? Now we can find the limit as n goes to infinity of 2n over n plus 1. Setting this to infinity, we will get infinity over infinity, which is L'Hopital's, right? So we can simply get the derivative of the numerator. The derivative of 2n is 2. The derivative of n plus 1 is 1. And so the limit is equal to 2, which is finite and a positive value. So because the series converges, then the series in question converges as well.